Hello everyone, welcome to RUIYI channel. Today's topic is why thin wall processing is difficult. First, let's understand what thin wall parts are. Thin wall parts in the manufacturing industry usually refer to parts with a ratio of wall thickness to axial or radial dimension greater than 1/10. These parts have a stable structure and maintain strength and precision while reducing the weight of the parts. With their unique structure and performance characteristics, they play a vital role in modern manufacturing. Thin-walled parts have a wide range of applications, covering many high-precision and high-demand fields. They play a key role in many fields such as aerospace, medical, precision instruments, robotics, automotive industry, and electronic equipment. In the automotive field, thin-walled parts are widely used in engine blocks, body panels, and other lightweight components to improve fuel efficiency. In electronic products, thin-walled parts are lightweight and durable. The shells of smartphones, tablets, and other portable devices all use thin-walled parts. Thin-walled parts can be divided into round, shell, and flat types according to their shapes. They can be divided into aluminum alloy, titanium alloy, composite materials, etc., according to their materials. They can be divided into frame, whole wall plate, beam, curved surface, etc., according to their structures. First of all, frame parts. As a typical part of the fuselage structure of aerospace vehicles, it is the main force-bearing part of the fuselage's transverse structure, and also the main structural part that constitutes and ensures the radial posture of the fuselage. Its structure consists of the workpiece outer frame surface, inner frame surface, and reinforced structural web. The frame structure is composed of webs, and its wall thickness ranges from 1.5 to 2.0 millimeters. The connection parts of the frame parts generally adopt a groove combination or a plane combination, integral wall panels. They are composed of ribs, skin fins, edge strips, etc. They are widely used in aerospace load-bearing thin-walled parts, such as wings, tail fins, and longitudinal fuselage structural parts. Compared with traditional riveting or bolting, integral wall panels have the advantages of reducing the number of parts, reducing assembly processes, and improving surface finish and fatigue resistance of parts, beam parts. With the continuous improvement of aerospace performance, beam parts are not only required to have higher strength and stiffness, but also to reduce mass to meet the performance requirements. The frame structure is more complex. According to the cross-sectional shape, it can be divided into I-shaped, U-shaped, and even more complex special-shaped cross-sections. Figure 3 shows a typical beam part, complex curved surface parts. This type of parts has the characteristics of complex shape, structure, and high processing precision. With the continuous development of aerospace vehicles, there are more and more curved surface parts, the most representative of which are impellers and blades, which are important parts of aircraft engines. The material used for thin-walled shaft parts is too thin and is very sensitive to temperature changes and external impacts. Structural aspect. In milling processing, as the wall thickness of parts continues to decrease, the relative rigidity becomes lower and lower, which easily generates cutting vibration and deformation and cannot guarantee the processing stability and quality. Functionality. The processing of thin-walled parts must not only ensure high processing accuracy, but also require high assembly accuracy in joints and other parts to ensure that the parts have reasonable assembly performance and meet use requirements. Material. Thin-walled parts are mostly made of high-strength aluminum alloy, titanium alloy, or high-temperature alloy. Whether it is easy-to-cut materials, such as aluminum alloy, or difficult-to-cut materials, such as titanium alloy, deformation problems are more prominent. Thin-walled parts usually have the characteristics of complex structure, large volume, etc., and high processing precision is required. However, during the manufacturing process, due to low rigidity and high metal removal rate, the workpiece will produce large deformation under the action of cutting force. After the processing is completed, the elastic deformation is restored, resulting in part of the material cannot be removed, and manual polishing is required, which greatly reduces the processing efficiency. During the machining process, the cross-sectional size and profile size of the workpiece vary greatly, and the rigidity is getting lower and lower. Not only does it cause overall deformation, such as bending and torsion, but it is also easy to cause cutting vibration, resulting in a decrease in processing precision and surface quality, seriously affecting its performance, and even causing parts to be scrapped. The 5 factors that have a greater impact on the deformation of thin-walled parts during machining are cutting force and cutting heat, workpiece material properties, clamping conditions, residual stress and tool trajectory, cutting force and cutting heat. In milling processing, due to the poor rigidity of thin-walled parts, the deformation caused by the milling force consists of 2 aspects: extrusion deformation of the workpiece, rebound deformation, tool deformation. The deformation trend is difficult to predict. In addition, due to the friction between the chips, the front and rear faces of the tool face, and the machine surface during deformation, the temperature distribution between the machine surfaces of the workpiece is uneven. The inner layer of metal hinders the trend of surface volume expansion. This obstruction causes thermal stress on the surface of the part. Under the action of cutting force and cutting heat, the stress distribution of the workpiece is affected, aggravating the deformation of the part and making it difficult to guarantee the processing accuracy. Workpiece material characteristics. Thin-walled workpiece materials are generally aluminum alloys, titanium alloys, or high-temperature alloys. Due to the small elastic modulus of the material, the specific strength of the material is easy to rebound during processing, resulting in part deformation. For the same material, as the size of the part increases, the rigidity deteriorates, and the asymmetry of its structure will lead to greater processing deformation of the part. Clamping conditions. The fixture is the bridge connecting the parts and the machine tool. The function of the fixture is to position and clamp the workpiece. For thin-walled parts, due to their thin walls, the workpiece will undergo corresponding elastic deformation under the action of the clamping force, thus affecting the surface shape and dimensional accuracy of the workpiece. Residual stress. Residual stress includes 2 categories: initial residual stress and processing residual stress. Initial residual stress refers to the uneven elastoplastic deformation of the material caused by the external force or uneven temperature field of the blank during the manufacturing process. Processing residual stress is the residual stress existing on the processing surface during the machining process. Due to the action of cutting force and cutting heat, the equilibrium state of initial residual stress is broken, and the workpiece re-equilibrates the internal stress through deformation tool path. As the machining process proceeds, the material is gradually removed, the workpiece becomes thinner and thinner, and the rigidity becomes smaller and smaller. Under the action of cutting force and cutting heat, machining residual stress is generated. In summary, it can be seen that in the milling process of thin-walled parts, due to the low stiffness of thin-walled parts, elastic deformation is easy to occur under the action of milling force, resulting in tool jamming, which causes friction between the tool surface and the machine surface, which not only affects the accuracy and quality of the machine surface, but also reduces the life of the tool. With the continuous removal of material, the decrease in workpiece stiffness, the release of residual stress, and the re-establishment of balance, different processing conditions, and other factors will have a great impact on the final deformation of the workpiece. Analyzing the factors that affect the machining deformation of thin-walled parts is of great significance for the prediction and control of machining deformation. How to control and reduce deformation during thin-walled processing and improve the quality of parts. We will give you a detailed answer in the next video. If you think our video is helpful to you, don't forget to like and collect it, and subscribe to our channel.